Yes. Yeah. So, hello everyone. I'm Tianxin. I'm from TUE. So, and I'm also a postdoc. So you can see that I'm a last-minute speaker. And yeah. Anyway, I'm happy to be here in this wonderful blue hall, and also with this like pencil-shaped handrails, if you haven't noticed them. So let's get started. My talk is about pets in the real world, and there's a black cat here, so such a good coincidence. So how many of you own a cat or own a pet? Okay, quite a few. I don't. So this is not about the real pets. So it's more about the privacy-enhancing technologies. So who am I? I'm a postdoc working on pets. For my PhD, I work on search encryption, and in my postdoc, I work on something biometric authentication, and also a bit on private set intersection. Okay, so let's just motivate it with this news. So I think many of you already know that the US administration use a Signal knockoff app, so which has recently got hacked in 20 minutes. Sounds good news. Okay, so this app is called Talent Message. So it's a knockoff of Signal. Because it's a knockoff of Signal, for sure, we may think, oh, Signal maybe it's the best if we want end-to-end secure communication. And there are other candidates around. So there's Telegram, and WhatsApp. And then you may wonder, what's the best, right? So in order to say what's the best, definitely not the features, like because if you know that Telegram actually doesn't enable end-to-end encryption by default. So but it offers a lot of social features, which is really nice that Signal is lacking. But because we are cryptographers, we want to learn more about the security side of these apps. So before we analyze it or find a way to compare them, we need to define security. So just think of the traditional encryption scheme. If I want to talk to Bob, I want some secure communication, then first is the confidentiality. It's more about the privacy side of the data. That's quite straightforward. And then we may want integrity, which guarantees that there's no adversary that modifies the encrypted traffic. However, it's much more ambiguous to define other functionalities. So what are the suitable security notions with respect to these other functionalities? So I already mentioned that there's a lot of secure communication tools out there, and we may want to build more pets, privacy-enhancing technologies. So this is so how do we build it? Is it through black magic or not? The good news is we actually have a standard approach that is called a provable security approach. So for this approach, we do the following. We define syntax and functionality. As usual, we consider Alice, who is interested in talking to Bob. Yeah, why I introduced Alice here is because that's how I get you interested in some boring topics. Okay, so this is more about the syntax or functionality. So we want some secure communication channel between Alice and Bob. But I didn't mention anything about security yet. So because we want something guaranteed on the security, then for sure we need to model an adversary, so Eve in this case. Okay. So the next step is usually we need to define what is secure related to the functionality. And then we propose a construction, prove the security of the construction by reducing it to some hardness assumptions. That's usually some mathematical problem. For example, some classical assumption that it's hard to factor in a large number into the product of two primes. And yeah, I also have Doge here because you see, this approach, you actually define what is secure related to functionality. So it's you, the cryptographer, define what is secure. Sounds quite suspicious, right? Okay. I already mentioned something about confidentiality and integrity. Those are quite standard notions. But in paths, we really consider something that is not that standard. So we need to first define some, say, security property. And here I want to introduce a property called anonymity. And anonymity has been used in digital payments because we want something that is untrackable. And there's a Zcash and also Taler, which is a GNU project on digital payment system that guarantees the anonymity. Then we have electronic voting. So also guarantees the anonymity for the voters. So it's hard to link the votes with the voter identity. And there's a system called Helios. This is actually used in the IACR when they do the elections. So yeah, sure, we are cryptographers, then for sure we should be the first to actually use something like electronic voting. Okay. And anonymity also used in like authentication tokens. Usually is some, say, user want to get the tokens first and later dispense them and to get in to a secure system. So later on, it kind of guarantees some anonymity within a set. Okay. So how do we build something like this? Because before I only talked about, I'm considering a large protocol, right? But I want to motivate it with a much simpler case that's more like primitive. Okay. So essentially, how we have this amazing functionalities that are listed there is we used it through built through a signature scheme that is called blind signature. So let's just look at how do we define blindness or blind signature with respect to signature, which most of us are more familiar with. So for the signature scheme, usually the signer knows what they're signing. But for the blind signature, by this blindness means the signer, when it wants to sign the message, it doesn't know the message. Okay. So as already mentioned, for proof of security, you would have the syntax, which essentially is an API that provides a set of algorithms for the users. So for the signature scheme, there's three algorithms: key generation, which generates a secret key and public key. And there's a sign, which signs the message with a secret key. And verify, which you can verify the signature using the public key. Okay. Because this is a blind signature. Sure, we have the blind there, is we want to blind message before sending out to the signer. So this is the additional algorithm there. So we need to define what blind is here. And then because we have signature scheme, right? So ideally we want signature scheme is if someone doesn't possess the secret key, you just can't forge a valid one. So that's the unforgeability property here. And sure, because of blind signature, later on, when you unblind the thing, it's still a valid signature. So the unforgeability still holds in blind signature setting. But other than that, we need to model what's blindness? What's anonymity? So usually there's a notion called unlinkability. In a way, it's more like formally to define how can you, with this blindness, you just can't link the transcripts and the signatures with the messages that have been signed. So this is unlinkability. So you see that how do we define blind signature from signature scheme? Okay. Then the question is, it seems rather straightforward, right? Let's just build paths, a lot of paths. Okay. This is a picture taken by some Twitter user, because that time was still Twitter. It was on 2019, January 5th. Just remember the year. And this picture says, it's an advertisement by Apple. What happens on your phone, stay on your iPhone. iPhone for sure. Sounds great. And then there's recent news, which happened last year, 2024, December 3rd. That's called enhanced visual search. So I didn't take this picture because I don't own an iPhone, but this was taken by a user that actually noticed during the latest update to their iOS system. This functionality actually was default to be on. So the user just turned it off but took a screenshot. But the main point is this is by default was on. And let me just read this. So this enhanced visual search allows this device to privately match places in your photos with a global index maintained by Apple. So you can search by almost any landmark or point of interest. But remember, what did Apple say in 2019? They say, what's on your phone, stay on your phone. But how about here? They are matching to a global index. How can you match something to a global index? For sure, you need to send something, right? So it kind of raises a question. So what's the privacy guarantee of this? Luckily for us, there's an academic paper, which was on arXiv. I haven't followed this, whether there's update to this or not, but it was on arXiv. It actually analyzes or proposes a scheme used by Apple. So this is called scalable privacy search with Wally. So a nice name. And then okay, so it's really unclear here, but so there's two main primitives or building blocks that Apple uses to build this scalable privacy search. First I want to say, this is a really impressive efficiency. So they can do this private search, so that you can do 8 million queries in 117 minutes. So this kind of, if you convert to milliseconds, it actually means that for every query, it takes around 0.9 milliseconds. It's really, really efficient. Trust me, because I spent all my PhD working on search for encryption. So I definitely know this, this would be really, really nice. And it's also technical challenging because the setting I was working on is your personal data. So you know your data and you have a secret key. And later you send it to the cloud, encrypt it to the cloud, and then you search with your secret key. But here's Apple doesn't know your secret key, right? So they somehow managed to do this and with great efficiency. So what techniques they're using? One is called private information retrieval, and the other is called differential privacy. So this talk is mainly about knowing different primitives and some security guarantees of these primitives, and something about the marketing claims and the user perception of privacy. Okay. The security guarantees. Let's just be kind of abstract. We have a security level here. So suppose I'm just storing my plain text data. Sure, there's no security, it's plain text, right? But ideally, if there's a perfect scheme there that can encrypt my data and also provides good functionality, then maybe I get the maximum security. But because we want deployment, and usually the security and efficiency are orthogonal to each other. So for the deployed system, maybe you can just get half of the security. Okay, so let's introduce Alice here again. Suppose Alice is a user of iPhone, and in her view, there's a threshold. So if the system that or the software that Apple provides, the security level exceeds to a certain threshold, maybe she's happy to get enrolled in the software and just to share the data in the encrypted form. Suppose her threshold is a green line here. Okay, good, right? Because that's actually below the what is deployed. And we have Bob. Bob is more privacy sensitive in a way, and he is actually wants something that's more than what is deployed. Okay, so likely he would not want to share his data. But there's Doge. So Doge here is, you can think of it as a marketing person, because you want to motivate the scheme and to let more people use it. Doge may claim actually have this maximum, or not maximum, it's a great security level and with a great efficiency. And if people believe what Doge says, sure, maybe just in this example, both Alice and Bob would be happy to share their data. Okay. This is a general picture of the privacy perception of the users and what is provided by the system. And you can see there's definitely something going on with this. But I already mentioned there's two things, right? One is differential privacy. So maybe let's just dive into this a bit deeper. So what's differential privacy? So this is really good. I don't know, it's kind of a buzzword in recent years. And there's a lot of papers around and also a lot of systems that claim they guarantee differential privacy. So what's that? Maybe I should just rephrase it in a way that is actually much easier to understand other than the differential privacy. This is, to me, is kind of abstract word, right? So I would actually call it as membership privacy, more like individual membership privacy. For sure, you can have group privacy as well, because you always have some parameters to tune for differential privacy, but let's just consider this really simple case. So for individual membership privacy, what does differential privacy give us, or theoretically, what it guarantees? So usually it's like this. If I prove certain mechanism is differential private, it means that for arbitrary neighboring databases, meaning that there's arbitrary two databases that only differ by one entry, if I run this DP algorithm on top of these two neighboring databases, then it yields similar output. So you see that. It means that whether a single data point, whether it's in the database or not, the output doesn't change that much. It's really nice, right? It kind of intuitively captures that if some algorithm is DP, it means that, okay, if I'm Alice, I'm involved in this, it gives me deniability, right? Because it means that I can say, you are not certain that for sure I'm involved in this data set. So I can always deny that my involvement in this data collection. Okay, great. And then let's look at, because this is more an informal way or something I summarize. I just want to give you a more certainty that this is actually what they claim in the paper. Let's just look at the first paper that introduces differential privacy. So this is Cynthia Dewar and others. This actually differential privacy notion gives Cynthia Dewar the Golden Prize. And if you look at this snippet, let me just read it out. In this paper, we consider general functions f mapping the database to vectors of reals. What does it mean? It means they want to have algorithm to compute certain statistics on the data sets. We prove that privacy can be preserved by calibrating the standard deviation of the noise according to the sensitivity of the function f. This is the maximum amount over the domain of f. That's any single argument to f. That is that any single row in the database can change the output. So it's not that clear here, but it kind of introduced multiple entries here. So, but what does it mean, right? Yeah, that's the next question. What does it mean? Like I already said that it kind of guarantees that the output, if one person's data's contribution, you kind of collaborating noise, meaning you're adding the noise to the output, that guarantees DP. Seems really nice. It has the individual membership privacy and deniability. But what does it mean semantically? Because we're all familiar with semantic encryption or the, say, in-CPA definition. So we actually want something that to say the ciphertext only leaks the length of the message, but it doesn't leak anything about the message. But here, you see, the differential privacy doesn't tell us anything about the semantic security. It only tells that my data doesn't change the output that much. But can you learn something from the output about us, about my data? Sure. Why? Because if it can't learn anything about us, why the company use it? Right? The company's goal is to conduct statistical analysis on the data with some privacy. So for sure that this data, even with the noise added, should give some statistics about this population or this data, right? So it reveals something. So for sure it's not a semantic secure. But how? So let's just maybe just think of the really concrete example, and you would then maybe can have a different view of differential privacy from now. Okay. So this add noise. If you recall that we have this sensitive function, which is this f is the mechanism or algorithm, right? So you first have this sensitivity definition here. It means that by adding or deleting a single entry of the database, the data set, if you run f over the data set, this output change. A concrete example is just think of count. So the one single person only contributes to count one. So in the count example, if I want to count how many smokers in the population, this sensitivity is 1. Okay, and then there's a privacy budget. So you may heard of this as something when you define differential privacy, because essentially it's a two-parameter notion. It's called a delta epsilon. The delta is, as usual, is kind of failure probability, but epsilon is a privacy budget. So this thing is actually something involved in the security definition. You can think of it as although it's called a budget, but reversely, you can think of it as the leakage. So it's something that for every DP algorithm that you run in once, then you leak something. So after a certain point, if this you reach to the epsilon, for sure you need no longer perform anything, even it's DP on this data set, because it means that it will reveal more information and it's no longer guaranteed by this epsilon delta definition. Okay, so I already mentioned that the DP, making something DP is actually really simple. So for this example, if we just have this count, we actually first compute a mean and scale. The scale means it's a variance, is the same in the following way. So mean, mu, and B is equals to delta F divided by epsilon. Okay, the noise is some Laplacian noise, which has a mean mu and scale b. And let's continue the example. Let F be the counter of a smoker. And I already mentioned that the delta F, this sensitivity is 1. And I put privacy budget epsilon equals 2 here. It's not something that I made up. It's actually, there's reference to that's what Apple uses in anything related to the health data analysis. So epsilon is set to 2. Okay. So if we just plug in the numbers, we get mu equals to 0 and scale equals to 0.5. And yeah. And then if we plot something like what's this distribution? So this the you can think of the x-axis is what we actually add to the noise, add to the output. And the fx is a probability density function. And you see that the noise is concentrated at 0. It means likely it doesn't add anything, but it's still dp, it still satisfies this nice notion, right? Epsilon equals 2, this notion. Doesn't sound right? So likely for differential privacy, you plug in this number and essentially, I just add something like -1, +1, or 0 to my count. And yeah, you have this notion, but doesn't sound like you actually have a great improvement on plain text. But it has a nice probability, it's composable, it's provable, and it's really easy to implement. But we probably are skeptical about this. Okay. That's that. I already mentioned there's the other thing, it's called private information retrieval. So this is a wonderful primitive that was introduced in 96 or 95, but that's the first paper was more about the information theoretic. What I cited here is the 1997 paper that's the first to propose a single server private information retrieval primitive in the computational setting, meaning that you always have some computational assumptions, meaning that you quantify the power of the adversary. You can't let them to do the unbounded computation, right? So similar as before, let's just look at the snippets here, because I already mentioned that for probabilistic security approach is you always have some syntax, and the syntax is not clearly defined here, but because it's an old paper. But from the correctness, we actually can see what's the syntax here. Okay, so the syntax, we have this correctness. It says for any n-bit input string, x given to database, which means that the database is actually n-bit input string x. And there's security parameters, just ignore it. And then there's a user or client's input, right? So the client's input is actually I, which is the ith bit of the n-bit string. So the output will be xi. You see, this private information retrieval definition, the functionality is there's a public database out there on the server, and the user query or encrypted query is on a certain index of n. And I didn't put anything here, but it guarantees the query privacy. So it's good, right? Just think of what's the use case. If we have some database or other than this n-bit string, if we have the user that have a private keyword instead of this index, then this kind of guarantees that it has query privacy. Okay. But the message length is not in the modeling. Why? Because we already assume that there's n-bit input string, and I'm accessing only 1 bit. So the message length is fixed. If it's fixed, it actually means that it's not in the modeling. That can be a problem. If you recall the Doge slide that said, what's secure? So actually the cryptographers define what is secure. By this security model, there's no message length. So kind of assume that I'm working on a database with every message of the same length, and it provides query privacy. Okay. So wait, what does it mean? Yeah, what does it mean this message length is not there, or it's not in the secure modeling? Is it fine, or maybe we can just use it, right? Well, let's just take a detour. Because I already mentioned that I work on social encryption during my PhD. I'm using encrypted search here is because it's more generic. There's other areas that call structured encryption, and we kind of collectively call it encrypted search algorithm. So let's take a detour to look at an area called encrypted search, because you will draw some conclusion yourself that what's the problem with the private information retrieval there. Okay, for encrypted search, usually it's a protocol run by two parties. One is the client, and the other is server. I already mentioned that private information retrieval usually is much harder to achieve because you run your queries or private queries on public data. But for encrypted search, we always assume that the client has their own data and upload to the cloud. And it's kind of a reasonable setting as well. Just think of Google Drive or whatever cloud storage you're using, and you want to do some encrypted searches on top. Okay, so we have these two parties. And as usual, let's just introduce the syntax of the encrypted search. So the clients run some setup algorithm on their database, and it outputs a key and encrypts the database. I just ignore the key generation. It's kind of a part of the setup algorithm. And then the client sends the encrypted database to the server. Later on, it can run a query algorithm with the server. So this is written in a way that it can be interactive or non-interactive. It doesn't matter. By the end of the protocol, it outputs the result to the server side. Sounds good. And we have this query algorithm here. As you can see, that the query algorithm takes as input the secret key and the queries, right? So for query privacy, sure, we just don't want anything that to reveal about these queries. And for the data privacy, the data actually we kind of specifically mean that it's the content of the database. We still don't want the server learn about the data. Okay. And because I then said that if we follow the proof of security approach, the next step is we need to define security. But define security is in a way that you actually need to model the adversary, right? That's quite essential. So just think of all the data breaches happening around the world. It's actually kind of reasonable to model it as a snapshot adversary. So what does it mean? It means that there's some adversary that steals the database, the encrypted one. And in this particular setting, it's a snapshot of the encrypted database. And the adversary's goal is to, can I actually learn something about the queries? Is anything actually stored besides this encrypted database about the queries? And can we actually hide the content of the database from this type of adversary, right? So these are the two privacy goals here. And under the stretch model that we have the snapshot adversary steals the snapshot of the encrypted database. Okay, sounds good. But can we have a stronger model, a stronger adversary? So indeed we have it. So it's called a persistent adversary. It means that in the cloud storage or whatever encrypted database that's stored on the cloud, we actually model server as a not a snapshot adversary, but a persistent one that is capable of observing the traffic. So before it only has access to a snapshot of the encrypted database, but now we actually have a stronger model that the adversary has access to the traffic. Okay, but in this setting, we just make the adversary power stronger, but still we want the same goal, right? So we want the query privacy that hide the queries, and we want the data privacy hide the data. Okay, good. Oh, okay, this is a timeline of social encryption. It's kind of started 2 decades ago by Tianxin and others. The paper on such kind of it's more like there's no security model in there, but it has some concrete construction. Hand waving proofs and there. Okay, then there's a line of work which like started from this practical construction that is already useful, and then for sure people think, oh, you have queries, I want to do more than exact match. Can I do more queries? Can I run SQL operations on top of encrypted database? Can I do everything the same as a plain text database? So people or users have this kind of request, right? So that's actually the focus of, you see there's 2006 to 2013 and all good. So this have a lot of various such encryption schemes. But let's just look at what's the end part of this arrow here. So it's like starting from 2018 to 2024, there's some like schemes there, but there's things like called leakage suppression, ORM-based approach, volume hiding. So what's this about? So you see, this is no longer about functionality, because already kind of exhausted doing all the fancy functionality, but here, leakage. What's the leakage? What's volume? It's actually message leakage. The length of the queries, the length of the response, so this thing. And what's ORM? It's called exit pattern, right? So ORM is oblivious RAM. It's kind of model some memory blocks, and you kind of hide your accessing which one. So that's called oblivious RAM. So this is all about how can you strengthen such encryption to hide this leakage. So why? The reason is encrypted search is really hard. So because for the theoreticians, or when we just started looking at the schemes and build things, we are living in a bubble. But in the real world, the bubble may burst. So that's what's happening with such encryption as an area. So starting from 2015 or later, so that was a good time to start your PhD. And all the leakage abuse attacks just appeared. So this actually means that like there's two groups of people. One is I want to strengthen self-encryption schemes. I want to build schemes that suppress all the leakage. And there's another group of people. Oh, given this leakage, how can I cover the queries? How can I cover the data, right? Sometimes it's good, but sometimes it's not that good. I would say why? Because usually when we work on text or when we work on constructions, we just have some assumptions that may not hold in practice, right? But you can always claim that my attacks are better, achieve better query recovery rate, in spite of it actually has a really unrealistic assumption. So that's kind of problem. But here, I will just briefly discuss what we found. So this is called MongoDB query encryption. So this was introduced in 2023 by MongoDB, who is the fifth largest database vendor. So they were the first to actually deploy such encryption in the real world. Before, we were just working on fancy theoretical schemes, and we are working on theoretical attacks, but this was the first one that actually deployed something in the real world. Okay, so MongoDB query encryption is a, let's just quickly look at what it's about, right? Okay, so think of, let's start with an example. Let's consider there's an extreme database which has data on the Springfield. And so we have two jobs. One is a nuclear technician, and the other is a CEO. And for the MongoDB database is a unrelated database, so it's more like a JSON, a collection of JSON documents. So So we have Homer Simpson as a nuclear technician, Lenny Leonard as a nuclear technician, and Charles Burns as the CEO. So this database only contains 3 records, which is a bit extreme, but it's fine. So suppose we are just working on equality search on the job field. So we want to search I want to search who is the nuclear technician, who is the CEO. And for sure, if we don't build anything that's extra data structure, you would need to do the linear scan. It's not good for efficiency, right? So for real world, we definitely need something that is really efficient, something like 0.9 milliseconds. And then usually in the plain text database community, so we have some data structure called inverted search index, is that we group all the field values that are equal. So here the nuclear technician maps to doc ID 1 and 2, is quite clear. And the CEO maps to doc ID 3. So this inverted search index allows us to have efficient searches on the job field. So for sure, because I'm saying this is secure encryption, right? So we suppose there's a scheme that just encrypt everything, and then also allows us to do efficient searches if we have this secret key to encrypt the data. So if we do this thing, it's an encrypted version, it's just secure encryption. Okay, but there's an issue here. Because before I said that my topic was discuss 2 concerns with definitions. One, differential privacy is there's a kind of different user perception of privacy here. But here I'm more about discussing the security modeling, because I would say that for our research or observations is that theoretical security modeling, there's a gap between what is actually available in practice to the adversary and what is modeled in theory. So the issue with secure encryption here is usually when you do this snapshot of the adversary, if you recall, it's the adversary get access to the encrypted database alone without these transcripts, because that means it's a stronger model. So for the snapshot of the adversary, it's only access to the encrypted database. And the theoretical modeling doesn't include anything with the queries transcripts. But in the real world is this secure encryption, this parts interacts with other system components. And this problem, because system components, you always have some logging system. For example, if you do replications and you want to ensure that your data or your system doesn't break, you need several copies and you want to sync across the copies, and you have this oplog. And by looking at this oplog, yeah, it's a mess here, but by looking at the oplog, you can actually identify certain algorithms that's run by secure encryption. And later you can group this thing using transaction IDs. And not good, because we will see. So this you group this. Before I said there's 3 documents in the database. So we have the 3 docs insertions, and then we have this tokens or whatever fields that appear in log. And then you actually can know that, oh, this 2 equals to the same field value. And then it actually maps to the encrypted document. So in a way, there's the edoc1, edoc2 contains the same field value, and edoc3 has a different one. And doesn't sound good because if you do classical crypto, you can do frequency analysis. And actually that's what we did. And it's like inference attack. And so this is kind of leakage that can be extracted from the logs that corresponds to frequency and correlation leakage. Suppose we know something about jobs or data about the Springfield before, knowing that there's 2 nuclear technicians and CEOs from 2024, and want to know something about 2025. Then there's a correlation, sure, I can recover. And there's more to that, because you see that each document, other than the job field, there's other field, right? There's a class of jobs. So for example, here we have nuclear technician, the class of jobs can be technician. So there's a correlation between the fields that is more powerful, so we can have more powerful attacks. So that doesn't sound good at all. Okay, now let's just move back to private information retrieval. And just pointed out this thing again, that by definition or syntax, this message length is not modeling, or is not in the security modeling or in the syntax. So we are skeptical about this. Then let's just go back to this again. So we have a differential privacy, we have the private information retrieval, and we have this high efficiency, and we're skeptical about this. Okay. So what else? For sure, I'm just running out of time, but there's a recent work by me and my former colleague that we analyzed that there's a security modeling that's a missing piece in the multi-party computation, is because you always guarantees that the input privacy from the transcripts, but you just don't discuss anything about the function output. So this can be detrimental in certain cases, and this would appear in this year's Usenix security, and it's already on ePrint. So if you are interested, just take a look. Okay. So then finally, the last slide, pets. This picture. And we have this picture. And we're not sure about it. Thanks, that's my talk.
Right. Since there's the morning, we are running at quarter past, we still have some time for questions. Are there any?
I'm sorry, I may ask a question. So, previously you showed this slide in 22, it's what Apple uses, and I didn't really get the takeaway, especially with this final slide where you say, oh, we're not sure. So, how should I interpret its values, epsilon 2? Is it good? Is it bad? Is it something you should be scared about, or is Earth would explode before that? How should you think about that?
So my personal opinion is there's marketing claims. So if we look at the curve encryption, for sure they will say, oh, we hide your queries and we'll have your data, and it's nice. You can trust them, right? So that, I would actually kind of advise in a way that just be critical about the security claims. It's maybe not that secure, but that's what they claim to be. Yeah. Because every user have different preference for their privacy levels. I already had that slide. So you have different threshold. So I wouldn't say, because some people would say, oh, I have nothing to hide, sure, right? So yeah, just go ahead and use those things. Okay. I'm not sure whether you are happy with the answer or not.
Yeah, I still mean sort of it just sounds like, oh, there might be a problem, but I don't have the tools to analyze things. I can first be oh, there's a problem, but it's kind of unsatisfactory, right? If I don't know what the next step would be.
Yeah, so the next step is, say for, maybe this is a really simple example, you can just turn it off, right? If you are not certain.
So, if there's no more questions, I have one. So you observed some issues with MongoDB, and I guess you entered some kind of disclosure process. Do you want to talk a little bit about that?
Yeah. So if people are interested, so we published the paper in 2023 on Usenix security for our analysis on MongoDB curve encryption, and we also disclosed this vulnerabilities we found with MongoDB. So the process was actually not smooth, because before, if you sometimes analyze real world systems and the security properties, usually when they build it, there's no cryptographers behind, right? So it's someone that is more on the engineering side, doesn't know about security. But the thing for us is that there are actually well-established cryptographers behind the MongoDB query encryption. And so that's what actually make things much trickier. And in the end, I would say our paper was published, and their marketing claim is still there, because we also send our code to them, and they indeed confirm our findings. But maybe quite good news is that all our analysis was done on MongoDB 6.0, and someone that look at our code also tried to run the same attacks on MongoDB 7.0 and didn't work. So they did do something that mitigate the attacks. So that's about it.
Okay, very good. Are there any more questions for now? All right, then I guess we can close today's program, and just a quick request. We do have a box for these name tags, and we want to collect them back, so please just put them back in the box. Yeah, and for that, I thank you for your attendance, and